Bismillahirrahmanirrahim. Dear students, I hope you're all fine and in the best condition of your health. So today we'll discuss about the ethers. Right, so as mentioned in the previous lectures, alcohols, phenols and ethers are very related compounds. So in case of alcohols, we have an OH to which one alkyl group is attached. So we consider alcohols as derivatives of water. We also consider alcohols as derivatives of alkenes. In case of phenols, we have an aromatic ring attached to an OH group, right? While in case of ether, we have an oxygen, and to both sides we have an alkyl or aromatic ring, right? So today we will discuss about the properties, preparation, and reactions of ethers. So the key concepts which we will discuss today are how we classify ethers, briefly about the nomenclature of this functional group, how we prepare these functional group, and the reactions of ethers. Right, firstly about classification. So ethers are classified as simple ethers or symmetrical ethers, and unsymmetrical ethers or mixed ethers. Right, so what do we mean by simple or symmetrical ethers is if the alkyl or the aryl groups which are attached to oxygen, if they are same, then the ethers are called symmetrical. For example, suppose we have two methyl groups attached to the oxygen. So if both groups are same, then this is symmetrical ether, or also called simple ether. However, if one group is ethyl and another group is methyl, since the groups are different, then the ether will be called mixed or unsymmetrical ether. Right? For example, diethyl ether. So we have this ethyl and ethyl group, right? Both groups are same, so this is a simple ether or a symmetrical ether. Whereas in case of this is ethyl group and this is methyl group, so since both groups are different, so this is called a mixed ether or unsymmetrical ether. Similarly, this is also an unsymmetrical ether because both of these groups are different. So this is about the classification of the ethers, right? So common names of the ethers are derived from the names of the groups which are attached to oxygen, right? For example, if we have an ethyl group and a methyl group attached, then what we do, how do we name them, is that we write the names of both the groups, which should be in alphabetical order, and the names of these groups should be separated, right? They should not be written as single word. So we have methyl and ethyl. Since E comes first in the alphabet, so name will be ethyl, methyl, followed by ether in the end, right? So the name for this molecule will be ethyl, methyl, ether. So suppose we have some so in case of the IUPAC name, what we do is that we use the term alkoxy first and alkene. So IUPAC treats ethers as alkoxy alkanes, right? So suppose the first part will be alkoxy and the next part will be what is that called? The alkene. So it's convention that the smaller part becomes alkoxy and the larger part becomes the alkene. For example, consider, so we have two groups, two methyl groups, these are same, so this is simple ether. So common name for that will be dimethyl ether, right? But in case of the IUPAC name, what we do is that we will consider one group as alkoxy, so we say this is methoxy and the next part will become the alkene, so there will be methoxymethane, right? Similarly here both groups are same, so this is ethyl group, this is also ethyl group, so what we'll do is say this is ethoxyethane, so this is the IUPAC name, but in case the common name will be diethyl ether. Now this is a mixed ether or unsymmetrical ether. So here we have a methyl group and here we have a propyl group, and the propyl is N-propyl, right? So in alphabets we have M first and P comes next, right? So according to the common name we will write as methyl, then separated by N-propyl followed by ether. But in case of the IUPAC nomenclature, since methyl is a smaller group, so we'll say methoxy, and that will become the alkane, so this will be methoxypropane, right? So this is methoxypropane. Then here we have a benzene ring, and here we have a methyl group, right? Since benzene is a larger group, so that will become the alkane fragment, and that will be written in the last, while methyl group, that will become methoxy. So we will write that as methoxybenzene, right? So the common name that will be written as methyl, since methyl comes first, M comes first, then phenyl, and then ether. So it's also known as anisole. Alright, so this compound has common name of anisole. Now we have another compound. Again, we have a benzene ring, and we have an ethyl group. Right, it's a common name. So we say that as not benzene, we say as phenyl. So the P of phenyl comes later in the alphabet. So we have the name as ethyl phenyl ether, and the common name for that is also phenitol. Right, this is phenitol, while IUPAC name will be, so the smaller group that becomes oxy, so that's ethoxybenzene. Now we have another group, that's again a phenyl group, and here we have a long chain, and this long chain of 7 carbons. So 7 carbons is called heptane. Right, so heptane is a larger group than benzene. So benzene has 6 carbons, heptane has 7 carbons. So the common name will be, so heptyl comes first in the alphabet, so this will heptyl phenyl ether, while according to IUPAC name, what good, so the smaller group will come first. This is a phenoxyheptane, right? So 1 is placed because this is the first carbon of the heptane that's bonded with the oxygen. Right, this is 1-phenoxyheptane. Now we have another one. So this is a methyl group, and this is isopropyl group. Right, again iso will not be considered. Right, so just ignore the iso and tertiary groups when you're considering the names, the alphabetic order. So here we have M, and here we have P of propyl. So since M comes first, the common name for that will be methyl isopropyl ether, while in case of the IUPAC name, the smaller group will become oxy. So this is methoxypropane, right? But since it's the second carbon of propane, that's a bonded oxygen, so we'll attach the 2 number. So that becomes 2-methoxypropane. Right, so here we have another structure. So we have a benzene ring, so we have a phenyl, and then we have 1, 2, 3, 4, 5. So we have 5 carbon chain, and this 5 carbon chain is isopentyl. Right, so the name for that will be, so this is P, so P comes later, but here also we have P. Right, but if you check that, so we have a larger group, so phenol, and we have pentyl ether. So you can use both groups interchangeably, but here we'll prefer the iso groups come later. So the name for that will be phenyl isopentyl ether. Right, but in case of the IUPAC, we'll say this is this is methyl butane. Right, so we have a straight chain of carbon, and 2, 1, 2, 3. So this is 3rd carbon. So this group is 3-methyl butane. Right, and this is phenol. So here we have 5 carbons, and here we have 6 carbons. This is smaller group. The smaller groups come first and becomes the oxy. So we will say 3-methyl butoxybenzene. So benzene name will come last. Now we have again, so now we have two ether functionalities. See, so we have a methyl group and we have two carbons, and then we have methyl group again. Right, so what we do is that since one carbon of this central carbon is attached with a methoxy group and the second carbon is also attached with a methoxy group, so the IUPAC name for that will be, alright, so the common name for that will not be applicable. So in case of that, so we have 1,2-dimethoxy, because one methoxy is attached to carbon number 1 here and the other methoxy is attached to carbon number 2 here. So this will be 1,2-dimethoxy, and then we have alkane here. So this will be ethane. So the name for that will be 1,2-dimethoxy ethane. Now we have a complicated structure here, right? So we have a, you can say, an ethoxy group here, and we have a full cyclohexane group here, and to this cyclohexane we have two methyl groups attached. So suppose we name this carbon as 1, so these methyl groups will be 1,1-dimethyl, and this will dimethyl cyclohexane, right? And this is this is ethyl group, and this ethoxy group is at carbon number 2. So by convention of IUPAC, the smaller group is considered as oxy. So we'll see that this is 2-ethoxy, and this will become the alkane. So this will be 2-ethoxy 1,1-dimethyl cyclohexane. So again, remember that whenever there is a name and number, so you have to place hyphen. So we have to place 2-ethoxy, then again hyphen 1, 1, so there should be comma between numbers. So 1, 1, then again hyphen dimethyl cyclohexane. So that's the way by which we assign IUPAC name to ethers. So now let's consider the physical properties, right? So the carbon-oxygen bond in ethers is a polar bond, right? So that means the ether have a dipole moment. They are not non-polar, but they are weakly polar, right? Since they are weakly polar, so their boiling points are not much higher. Just for comparison, we consider these different alkane, ether, and alcohols, right? So for convenience, we have kept the number of carbons same. So we have molecular weight almost same. So we have there a, you can say, pentane. So in case of pentane, the boiling point is 309 Kelvin, right? In case of ethers, the boiling point is 307.6, right? So you may say that boiling point of ether is lower than that of alkane as well, while in case of this alcohol of relatively similar molecular weight, the boiling point is 390 Kelvin. So there is a huge difference in the boiling point of ether and alcohol, although both have oxygen. And strangely, you can say that ethers and this alkane have almost same boiling point. The reason being that in case of ethers, there is no hydrogen bonding at all, or the hydrogen bonding is very, very negligible, right? So the higher boiling point of alcohol is because of presence of hydrogen bonding, right? Now we'll consider the preparation of ethers. So there are different methods for preparation of ethers, so we will consider only the methods that are normally used for laboratory scale preparation of ethers. Right, so we can, number one, prepare ethers by dehydration of alcohols. So D means removal, hydration means water. So if we have suppose two alcohol molecules and we carry out the dehydration, intermolecular dehydration of alcohols, then we can get ether. Right, so for carrying out the dehydration, we have to make use of protic acids. So we make use of sulfuric acid or phosphoric acid, right? So this reaction is very interesting because it can either result in dehydration means remove water, and will result in formation of an alkene. So this specific case is intramolecular dehydration. This is removal of water within the same molecule. And what we are interested in intermolecular dehydration, means loss of OH from one molecule and loss of H from the other molecule, right? So for that purpose, what we do is that we have to maintain lower temperature conditions in case if you want intermolecular hydration, right? So if you want to remove water molecule from two different molecules of alcohol, then you have to maintain a lower temperature. But if you want to carry out the dehydration within the same molecule, if you are interested in formation of alkenes, then you have to go for higher temperature conditions, right? So in case of we are interested in formation of ethers, so what we have to do is we have to maintain low temperature conditions and sulfuric acid as a catalyst, and under these conditions what we get an ether as the product. So mechanism of this reaction, that depends on substrate, right? So formation of ether is normally a bimolecular reaction. This is SN2. So S stands for substitution, and for nucleophilic 2 means two molecules. Since reactions involves two molecules, that's why that's a bimolecular reaction, right? So SN2 reaction mechanism is suitable if you have the alkyl groups with primary alkyl groups only, right? If both the groups are primary alkyl groups, then you have this method that's very suitable. Secondly, these alkyl groups should be unhindered. They should not have any steric hindrance. Thirdly, the temperature should be low. So these three conditions are very important. Number one, the alkyl groups should be primary. Second, the alkyl groups should not be hindered. There should be no steric hindrance. They should not be bulky. The alkyl groups should not be larger or very much branched, and the temperature should be low. So if any of these conditions are not fulfilled, you will not get ether. Instead, you will get the alkene, right? So normally the formation of alkene favors SN1 pathway, and this alkene formation is much more favored when alcohol is secondary or tertiary. This is important to note. So if you're going for formation of ethers, the mechanism is SN2, and primary alcohols favor the formation of ethers, while if you have secondary alcohol or a tertiary alcohol, then you will get alkene, and the pathway will be SN1, right? So temperature conditions and the nature of alkyl group is very important for this reaction. Okay, so consider the mechanism of reaction. So we have a primary alcohol here. So for easiness, we have started with this ethyl alcohol, right? That's a primary alcohol, right? That should favor the formation of ether. So the first step is that we add a strong protic acid. Suppose we have given each sulfuric acid. So sulfuric acid loses protons. This is the proton that was lost by the sulfuric acid. Suppose this oxygen will pick up the proton. So here this oxygen is acting as a base, right? So here we get an oxygen with a positive charge. So what will happen, that suppose another alcohol molecule with oxygen, now this oxygen will attack this carbon, right? So when this oxygen will attack this carbon, this oxygen with positive charge will be lost as a water molecule. So here we are causing elimination of water molecule here, and this oxygen is forming bond with this carbon, right? So again, remember that whenever the carbon-oxygen bond is broken, it means that molecule is acting as an electrophile, right? So this carbon is acting as an electrophile, and this oxygen, which is attacking this carbon, this molecule is acting as a nucleophile. So this nucleophilic oxygen will attack this electrophilic carbon, and the water molecule will be lost. So here we have this molecule again the oxygen with 3 bonds is having a positive charge, right? So what happens then, this proton will be lost again, right? So this proton is lost and we get an ether, and this H positive is recovered, right? So this was consumed during the reaction, it speed up the reaction and is recovered unchanged by the end of reaction. So here this proton is acting as a catalyst. So this is the mechanism for formation of ethers by dehydration of alcohol. So just keep in mind that when you have to synthesize ether from these alcohols, your alcohols should be primary and temperature conditions should be low, and the mechanism is SN2. However, when we use secondary alcohols or tertiary alcohols at high temperature, what we get is we get the alkene, not the ether, right? The second method for formation of ethers is Williamson synthesis. It's again an important method, and the importance of this method is that we can prepare symmetrical as well as unsymmetrical ethers both, right? So in this method, what happens that we take an alkyl halide, right, and we react this with sodium alkoxide, right? So alkoxide is a stronger base and it's also a good nucleophile, right? Alkyl halide has a carbon which is electronically deficient, right? So ethers containing substituted alkyl groups may also be prepared by this method. So the previous method, which was dehydration of alcohols that had limited use, that can be used only for primary alcohols, but Williamson's ether method is very important because you can make symmetrical or unsymmetrical ethers as well. Also, you can make use of primary alcohols, secondary alcohols, or tertiary groups, whatever. So whatever be the nature of groups, you can use them for Williamson's synthesis. So the mechanism of this reaction involves SN2 reaction, right? So SN2 means substitution, nucleophilic, and 2 molecules are involved, so that's the 2 it stands for. So the reaction depends on concentration of both primary alkyl halide and the alkoxide ion as well, right? So although we can make use of any alkyl halide, but the reactions are obtained best if the alkyl halide is primary, right? But in case of secondary and tertiary alkyl halides, then instead of along with the formation of ether, we also get the alkene as well, right? So we have some side products in case of secondary and tertiary alkyl halides. So again, for Williamson ether synthesis, although we can make use of any alkyl halide, primary, secondary, or tertiary, but we prefer the primary alkyl halide. And in case of secondary and tertiary, since elimination competes over substitution, so we have some side products as well. If we use tertiary alkyl halide, then the alkene is the only product and no ether is formed, right? Because alkoxides are not only nucleophile but also strong bases, so they react with alkyl halide, leading to elimination reactions, right? So tertiary alkyl halides, what they do is that they cause the elimination reaction, they don't go substitution reaction as well. So again, we will prefer the primary alkyl halide as well. So mechanism of this reaction, we have an alkoxide here, so we have sodium alkoxide. So sodium is a higher counter ion, so it will not be involved in the reaction, it will be present as such in the reaction mixture. So this is alkoxide, so oxygen is having a negative charge here. So this oxygen will attack on this R group, right, and the halogen will leave. This is general mechanism. So we will get an ether and we will get sodium halide. Suppose if this is chlorine, so we will get sodium chloride. Suppose that we have a tertiary alkoxide here, so we'll get this tertiary alkoxide that will attack this carbon, right, and the bromine will leave here. So we'll get bond between this oxygen and the methyl. So here we get this one. So you will try to name that molecule if you want to. So according to IUPAC name, the smaller group will become the oxy and the larger group will become the alkane, right? So if you say this is carbon number 1, this is the second carbon to which this group is attached, So we can say this is 2,2-dimethyl ethane, right? So this is larger group, so that will form the alkene, and the smaller group, so this group will be called as methoxy 2,2-dimethyl ethane, right? So here now we use the tertiary alkoxide, so reaction worked well, but when we use tertiary alkyl halide, what we get is that we get the elimination product, we don't get any ether. That's the trick. So you can make use of any alkoxide, you can make use of primary alkoxide, secondary alkoxide, or tertiary alkoxide, but when you use alkyl halide, try to prefer the primary alkyl halide. In case if you use tertiary alkyl halide, then you get the elimination product as well. But if you use primary alkyl halide, ether formation is only the stable product. However, it doesn't matter which alkoxide you prefer. So these are two methods which are normally used for the formation of ethers. That's dehydration of alcohol and the Williamson ether synthesis. Now we consider the reactions of ethers. So it's important to note that ethers are least reactive of all the functional groups. So you may have seen that ethers are used normally as solvents. Why they're usually not used as solvents? Because they are not reactive. So their least reactivity makes them a good option for being used as solvent. Also, they're volatile, so their boiling points are lower, so it's easy to remove them from the reaction mixture, right? So the reactions of ether, firstly we consider that if we break the carbon-oxygen bond, what happens, right? So if you have to break the carbon-oxygen bond, since ethers are least reactive, you need to give very harsh, drastic conditions. So if you are using milder conditions, then this bond cannot be broken. So if you have to break this carbon-oxygen bond in ether, so you have to make use of strong conditions. And by strong conditions, which means we have to make use of excess of hydrogen halide, right? So what we get is that ethers, when reacted with excess of hydrogen halide, that result in formation of this breakage of this carbon-oxygen bond. So we get an alcohol and we get the alkyl halide here, right? So you can just compare this reaction with alcohols. In case of alcohol, when we react the alcohols with this hydrogen halide, which Ajax, alcohols get converted into alkyl halide plus water. In case of ethers, we get alkyl halide, but instead of water, we get alcohol. See, that's the process. This alcohol, if you are using this excess of alkyl halide, so this alcohol will get converted into alkyl halide as well, right? So what we get is that in general we say that when you are using ether and you are using excess of this hydrogen halide, we get these alkyl halide molecules. So initially we get alkyl halide with alcohol, and this alcohol, upon reaction with this hydrogen halide, is also converted into another molecule of alkyl halide. Right, so if instead of simple ethers, if we have alkyl halide ether, suppose we have an R group and we have a benzene ring attached, right? In that case, it's only the alkyl oxygen bond which is broken. So we don't break this oxygen and aryl fragment. So we don't break this bond. So it's only the bond between oxygen and R group that's broken, right? Reason being that if it's broken, then we get the phenol, and phenol is highly stable, right? So cleavage of OH bond in alkyl aryl ether results in formation of a phenol and alkyl halide, right? So if you want to check which hydrogen halide to prefer, always prefer hydrogen iodide. So hydrogen iodide gives the best reactions. Hydrogen bromide gives some better results, but not as much better as hydrogen iodide, while hydrogen chloride gives the least reactivity. Right, so in order to give the best results, so you have to give high concentration of hydrogen iodide and you have to maintain high temperatures. So under these conditions, you get the best result of formation of phenols and hydrogen halide. Okay, so suppose we have alkyl aryl ethers, right? So we have a benzene ring here. So in that case, what we get is the electrophilic substitution reactions, right? Again, we have oxygen here, just like in case of phenol, and the oxygen has lone pairs. So this oxygen makes electronic density rich at ortho, you can say at ortho and at pair position, right? So this negative charge shows the electronic density is rich at these positions. So since the aromatic ring is electronically rich, it has higher electronic density, so electrophile easily attack on these carbons. So also electrophile will prefer to come at ortho or at para position because these positions are electronically rich, right? So this alkoxy group is ortho para directing and activates the aromatic ring towards electrophilic substitution reaction. So we'll consider some substitution reactions. Firstly, halogenation. So if we have phenyl alkyl ethers, right, they undergo halogenation on the benzene ring. Again, the product will be ortho and para substituted. We don't get any meta product. Suppose we are using anisole. So this is methoxybenzene, right? So the conditions are that we have to use the halogen, suppose bromine, and we make use of acetic acid. So acetic acid will act as a catalyst as well as solvent. So it has dual function. So ethanoic acid also means acetic acid, right? So here the acetic acid will act as a solvent and also as a catalyst. So normally we make use of iron bromide, FeBr3, FeCl3 in order to carry out halogenation on benzene ring. But in case if we have oxygen attached to the benzene ring, there is no need for these catalysts. So reaction works well in the absence of this Lewis acid catalyst because the benzene ring is already being activated by this methoxy, which is increasing the electronic density. So under these conditions, if you use bromine in presence of acetic acid, the para product is the major product, while other product is formed in minor amounts. So with anisole, we get 90% of the para product, only 10% of the ortho-bromo anisole. Okay, again, we are considering the aryl alkyl ethers, and for example, we have taken the example of anisole, right? So just like benzene undergo Friedel-Crafts reactions, these aryl alkyl ether also undergo Friedel-Crafts alkylation reactions and Friedel-Crafts acyl reactions. Since methoxy group is ortho-para directing, so these alkyl group or acyl group, they are added to ortho or para position. Right, so this reaction takes place in presence of Lewis acid as a catalyst, and the best catalyst for this is anhydrous aluminum chloride. Right, so just we see the examples. For example, we have this anisole and this is the methyl chloride, right? So we are interested in bringing that methyl on the benzene ring, right? So we have to bring an alkyl group on the benzene ring, so this reaction will be called Friedel-Crafts alkylation, right? The catalyst will be anhydrous aluminum chloride, and you may use of carbon disulfide as a catalyst, as a solvent. So carbon disulfide is a non-polar solvent, so in this reaction either we use ethers or we make use of this carbon disulfide as a solvent, right? So under these conditions, so since methoxy is ortho-para directing, so we get the methyl at ortho position and methyl at para position. So again, the para product is major one, or the product is formed as minor product. So get two products, as one is minor, which is the ortho product with 2-methoxytoluene, and in that case we have the major product. So in that case, okay, so with the same substrate we can also make use of this acetyl chloride, right? So this is acetyl group and to this is chlorine is attached. This is acetyl chloride. Again, the catalyst will be anhydrous aluminum chloride. Now we get the acetyl group at ortho position and acetyl group at the para position. So this reaction is very important in that sense, because by this method we can introduce a ketone onto the aromatic ring, right? So firstly, initially your substrate was an ether, but after this Friedel-Crafts acylation you have brought a ketonic group onto the benzene ring. So this reaction is important sense because by this we can bring a ketone onto the aromatic ring as well. So again, if we have some aryl alkyl ether such as anisole, we can carry out the nitration of this reaction. So in order to carry out this nitration, what we do, we need the nitric acid and also sulfuric acid. So in case of the nitration of phenol, we only used nitric acid, but in case we have carried out nitration of anisole, we have to make use of mixture of concentrated sulfuric acid and nitric acid. Otherwise reaction won't work, right? So this is the difference in the phenol and the ethers, right? Again, so under these conditions, when we use make use of nitric acid and sulfuric acid, mixture of these acids as catalyst, so we can bring about the nitro group at ortho position and at para position. So the para position isomer, this para isomer always dominates over this ortho isomer, right? So we get mixture of products with ortho as minor and the para product as the major product. So now it's important to note that so whenever these reactions we have considered for the alkyl aryl ethers, we always say that the ortho product is minor while para product is major. So why is that so? So in order to answer this question, just see the structure. So in case of the ortho isomer, say that we have two larger groups which are very close to each other, right? This is nitro group, that's not a smaller group, that's a big group. Similarly, this is a methoxy group, that's also a big group. So since these groups are very close to each other in space, they cause repulsion between each other. This is called steric hindrance, right? The hindrance or repulsion because of larger groups. This is called steric hindrance. So because of this steric hindrance, this molecule become unstable, right? Just consider them as two bushes, and these two bushes are very close to each other, so they stuck into each other, right? So in order to avoid the repulsion between each other, so this nitro group doesn't prefer to stay at the ortho position. Instead, this nitro group prefers to go at para position where there is no such repulsion, right? So it is because of this steric hindrance, this steric repulsion, because of which the ortho product is not formed to much extent. Similarly, you can say in the Friedel-Crafts alkylation, so here we have methyl group and methoxy group, right? So because of steric hindrance, this ortho product is not formed as a major product. Similarly, we can say this ketonic group, that's still a larger group, and this is a methoxy group. So because of the steric hindrance, the ortho product formed is always the major one, right? While the ortho product is a minor product, while the para product is the major product, right? So I hope you have understood about the ethers. So it's important for you to remember that ethers are least reactive of all the functional groups, and for the same reason ethers are considered suitable to be used as solvent in organic chemistry, right? They are low volatile, they are least reactive. Further, we have studied about how we classify them. So ethers are classified as simple ethers or symmetrical ethers and mixed or unsymmetrical ethers, right? So they can be prepared by dehydration of alcohols. So in case of ethers, you are interested more in the intermolecular dehydration. Well, if intramolecular dehydration occurs, then we get alkenes, not ethers. This is important. Among reactions, so normally the reactions involve the cleavage of carbon-oxygen bond. So in case if we have alkyl aryl ether, it's always the oxygen alkyl group that's the bond which is broken. We never break the oxygen and aryl bond because this oxygen aryl bond is much more stable because of formation of phenols. I hope you have understood all. This is the recommended book for this lecture. Thank you.